Today, Bayaw, I'm here to give an example from Chapter 11, the combined heat transfer. Consider steady heat transfer between two large parallel plates at constant temperatures of T1 is equal to 300 Kelvin and T2 is equal to 180 Kelvin that are L is equal to 2 cm apart. Assuming the surfaces to be black, emissivity E is equal to 1. Determine the rate of heat transfer between the plates per unit surface area. Assuming the gap between the plates is A. Filled with atmospheric air, B. Evacuated, C. Filled with fiberglass insulation, and D. Filled with super insulation having an apparent thermal conductivity of 0.0015 watts per meter degree Celsius. So this is the figure in this problem. Since the thermal conductivities are K is equal to 0.0015 watts per meter degree Celsius for super insulation, K is equal to 0.01979 watts per meter degree Celsius at negative 50 degrees Celsius, which is defined in table A15 in thermodynamics for air, and K is equal to 0.036 watts per meter degree Celsius for fiberglass insulation, which is defined in table A16 in thermodynamics. So, first, we need to find the heat conduction. So, the formula, heat conduction is equal to thermal conductivities times the area times T1 minus T2 over L. So, substitute. Heat conduction is equal to 0.01979 watts per meter degree Celsius times the area 1 squared meter times 300 Kelvin minus 180 Kelvin over 0.02 meter, which is the length. So since 2 centimeter, and this to convert into meter, so 0.02 meter. So our heat conduction is equal to 118.74 watts. Next, so to find the Q rad or the heat radiation, we have the formula heat rad is equal to emissivity times the surface tension times the surface area times T1 raised to 4 minus T2 raised to 4. So substitute. Q rad is equal to 1, which is the emissivity, times 5.67 times 10 raised to negative 8 watts per squared meter Kelvin raised to 4 times surface area 1 squared meter times 300 Kelvin raised to 4 minus 180 Kelvin raised to 4. So simplify. So our Q rad is equal to 399.75 watts. Since we have the Q rad and the Q conduction, so next, so the Q total is equal to Q conduction plus Q rad. So Q total is equal to 118.74 watts plus 399.75 watts. So add. So our Q total is equal to 518.49 watts. So next, when the airspace between the plates is evacuated, there will be radiation heat transfer only. Therefore, so our Q total is equal to Q rad. So Q rad is equal to 399.75 watts, which is this is the airspace between the plates is evacuated. So next, since there will be conduction heat transfer through the fiberglass insulation, so Q total is equal to Q conduction. So since our Q conduction is equal to Ka times T1 minus T2 over L. So substitute. So Q conduction is equal to 0.036 watts per meter degree Celsius, which is the thermal conduction of the fiberglass insulation times the area 1 squared meter times 300 Kelvin minus 180 Kelvin over 0.02 meter. So our Q conduction is equal to 216 watts. So next, since in the super insulation, we have the Q total is equal to Q conduction is equal to K times A times T1 minus T2 over L. So So substitute, Q conduction is equal to 0.00015 watts per meter degrees Celsius, which is the thermal conductivity of the superinsulation, times 1 squared meter, which is the area, times 300 Kelvin minus 180 Kelvin over 0.02 meter. So our heat conduction is equal to 0.9 watts. So this is the superinsulation heat conduction. Thank you for watching.